What is going on, guys? It's Calculus 3 here.
Well, I need a green tea too
What's your favorite
to cleanse my liver.
Oh yeah, that's what they want to hear. Really, I know. That's how all the YouTubers start their things. What is going on, guys? Blah 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 blah.
I can't stand listening to YouTube videos because they all sound the same.
It's like I watched FaZe.
And then you get those guys that think they know.
They all say, yeah, yeah.
You're watching the wrong people, man. I watch Vsauce. Who never does that?
My kids are obsessed with YouTube
Vsauce,
videos.
the physics guy. He's pretty cool. I'm gonna go see him live in a month.
What do YouTube guys do live?
Him and the guy from Adam Savage from MythBusters, they're coming to Durham. They're physics. They're physics people, and they're gonna do all these like things. Cool
Okay.
things. They said they bring 3 tons of their stuff. Adam Savage, yeah. Have you ever seen MythBusters?
Yeah.
He's the redhead.
Can be stupid.
Yeah. Jamie Hyneman was the other one.
Yeah. With the brain.
All right, so we've already started cross product.
Yeah, I don't watch that.
I don't watch it.
I watched one of the videos.
Pretty much all we've done with this so far is the calculation. We haven't really talked about what it's for yet. Somebody asked real quick at the end of class what the number means, and we said it was the area of the parallelogram. But there are a lot of other things that we could use the cross product for. So one way to do it was with the 3x3 matrix. And then from physics class, you've also learned just to memorize the formula, possibly. The 3x3 matrix does lead to the formula. So if we break this down with cofactor expansion, it turns into 3 2x2 matrices. Me? And once we get it finally down to this form, that's the one you might remember from physics class. Yes. It's not terrible to memorize that. There is a pattern to it. I've never memorized that. I've always done it with the 3x3 determinant. I don't care how you decide to do it as long as you know how to do it. So it's completely up to you, okay? So as long as you know how to find a cross product, wonderful. So just a quick little recap. We said that the cross product is also called the vector product. Because the answer is going to give us a new vector. And that vector has some important properties that we're going to have to use in the next section. U cross V is orthogonal to both U and V. So the vector we get back from doing the cross product is always something that is perpendicular to the two original vectors that got put into the calculation. Which means a cross product is always done in 3 dimensions. So U and V, any two vectors can define a plane, but then once we need to be perpendicular to both of them, we need to shoot out in a third dimension in order to be perpendicular to both of them. So this always has to be done in 3 dimensions. Bless you. All right, so just some quick little practice just to make sure we're all okay with cross product. We're going to do one quick cross product, and then we're going to go over some properties, some geometric and some algebraic properties of cross product, and talk about a couple of things that we can do with cross product. This section is not very long. Most of what we can do with cross product is going to be in the next section when we talk about lines and planes. So I'm going to give you guys a minute to try this. We want to find U cross V. And U is the vector with components -2, 1, 5, and V is the vector with components 3, 2, -1. I didn't believe Easton. So I prefer to do it with a 3x3 matrix, so I don't have to try to remember the formula. Always set it up with ijk on the top row. The first vector in the cross product goes in the middle row, and the second vector in the cross product goes in the last row. And then we do cofactor expansion across the ijk. And then for the determinant of the 2 by 2 matrices, we just do the product on the diagonals and subtract. So I got negative 11i plus 13j minus 7k.
Just forgot the one middle thing. I had minus
Change
13.
change the sign on the j.
So,
Change the sign on the j. Kirby, you okay? All right, so it's one thing to be able to just do the calculation, but obviously there's going to be tons of stuff that we want to be able to do this for. It's not very helpful just to be able to do some random calculation. What main operations are we performing when we do the cross product? Multiplication and subtraction. Yeah. In the 2 by 2 determinants, we're subtracting every time. Multiplication and subtraction. Because of the subtraction, if we change the order that those two vectors are in, it's going to change our answer. Because if you change the order of subtraction, it's going to change the answer. But it doesn't change the answer significantly, it just changes the sign. Because 10 minus 7 and 7 minus 10, the answer has the same absolute value, it's just opposite sign. So the same thing is true with cross products. So that's one of our properties for a cross product. We've got some algebraic properties and we've got some geometric properties. So U cross V is going to be exactly the negative of V cross U. And this has to do with the idea of that right-handed system. Because we're changing what vector we start at and which vector we curl to. And that's going to change the direction that our thumb is pointing in. Our thumb is going to be pointing in the exact opposite direction. We're still using the same two vectors, but we've got to flip our hand in the opposite direction. No, you're not just stupid. We're not distributing the negative? Is that what you're thinking? Distributing the negative and they'll all just multiply and cancel out?
I was just thinking like if UV was like 1, 2, 3, VU would be -1, -2, -3.
Right.
So if you had that negative, it would switch it back.
Nope. Because if U cross V, in order for them to be equal, we have to negate the other one.
I would say this.
No, you're fine. I understand what you're saying. So in order to make them equal, we've got to distribute negative into one of them. But you're good now, right? Okay. They'll always be exact opposite directions, and this has to do with that right-hand rule and the direction our thumb goes, because of which direction we're starting at and which one we're curling to. It does have the distributive property, and if you think back to algebra, we can distribute over subtraction. So even though our main operations here are multiplication and subtraction, not multiplication and addition, we can still use distributive property. So if we've got U crossed with V plus W, we could distribute this and do U cross V plus U cross W. So most of these properties, if you just think back to what would be appropriate in algebra and what algebraic operations are we using in this calculation, they fall right in line with what we would see in algebra. If we want to multiply by a scalar, we could do it after the cross product, or we could multiply either one of those vectors by the scalar before the cross product. It would not distribute to both of them because both of those operations are considered multiplication. It's two different types of multiplication, but you don't distribute across multiplication. So we could multiply by the scalar after the cross product or into either one of them before the cross product. Anything crossed with 0 is 0. And we think of 0 as being the 0 vector that has components all with values of 0. So one of the operations we're doing in the cross product is those multiplications, those crisscross multiplications in our determinant. So every single one of those multiplications is going to include a multiply by 0, which means all of them are going to come out to be 0. If you cross a vector with itself, you get 0. Which is interesting. But if you look at the formula, it makes a little more sense as to why. And then if you think of it in terms of a geometric aspect, we can see why as well. So for the I component, we're doing U2, U3 minus U2, U3. For the J component, we're doing U1, U3 minus U1, U3. For the K component, we're doing U1, U2 minus U1, U2. So all of the products end up the same, subtracting ends up 0 every single time. So algebraically, it's easy to see once we set it up, but also geometrically, the cross product is supposed to come out to be one unique vector that is perpendicular to both of these vectors. And these two vectors are supposed to define a plane. But because these are not two unique vectors, but one single vector, they don't define a plane. I've got one vector that's repeated twice. It doesn't define a plane. There are an infinite number of vectors that are perpendicular to that. And because of that, I cannot come up with an answer for the one unique vector that is perpendicular to both of them. We can't do it because I have not defined a unique plane by plugging two unique vectors into the problem. The last one is called the triple scalar product. And it's what happens when we mix dot product and cross product. And we want to use the associative rule of multiplication. And we just need to be careful with what the answers to these different types of multiplications are going to give us and what we are allowed to do. So the first one says U dotted with V cross W. And I've got parentheses around the V cross W. What kind of answer are we going to get from V cross W? A scalar or a vector? A vector. So this is going to be a vector. So now I've got a vector dotted with a vector, which is going to leave me with a scalar. So the overall answer is going to be a scalar. So if I wanted to use the associative property and switch the order that I'm doing these, I'm not switching the order that they're written. It's still UVW, but I'm going to group together U and V first. I can't leave the dot first and the cross second. I'm going to erase this in a second, but I just want to show you what would happen if I tried to. What is the answer to a dot product? A scalar. And we can't do a scalar crossed with a vector. We can't do that. So if I want to switch using the associative property, I have to also switch the operations. The cross product has to be done first. So I can switch the order that these operations are done in as long as I also switch the operations. So I would have to change that to a cross product and this to the dot product. The cross has to be done first because the dot product has to be done between two vectors. The cross has to be done between two vectors. And this is called the triple scalar product. and it has a geometric meaning, which we'll talk about in a little bit. It looks like it's two separate operations, but we can actually do the whole calculation at once. So those are some different algebraic properties. If you think about us using multiplication and subtraction as the main algebraic operations, and then also think about cross product as leading to vector answers and dot product leading to scalar answers. Hopefully most of them make sense. Some geometric properties. And then we'll look at a few more examples, and that's really all that's in this section. Section 5 is a whole lot more important and has a lot more stuff in it that we're going to want to use. So U and V are going to be non-zero vectors in space. Remember, all this stuff happens in three-dimensional space. And theta is the angle between U and V. A few of these we've already talked about, but it's good to just have them all in one list. So the first, probably most important geometric property that we're going to use over and over and over again throughout the rest of the semester. Every single time we say that we need an orthogonal vector. Remember, orthogonal just means perpendicular. We need to think cross product. Cross product will always give us a perpendicular vector. And that's one of the most important things we need to know about cross product, is U cross V is orthogonal to both U and V. Anytime we have a problem and we know that we need a perpendicular vector, almost always we're going to do a cross product. One of our geometric properties for dot product was that we can find the angle between two vectors. And there is a similar one for cross product. With dot product, it gave us the cosine of the angle, but with cross product, it gives us the sine of the angle. So the magnitude of our cross product is equal to the magnitude of each vector times the sine of the angle. But to use this formula, we typically move the terms around and solve it for sine theta and say that sine theta is the magnitude of the cross product over the magnitude of the individual vectors. That's how we wrote it when we did the dot product. We said cosine of theta is dot product over each magnitude. Sine of theta is magnitude of cross product over each magnitude. So cosine is associated with dot product, sine is associated with cross product. With dot product, we didn't have those magnitude bars because dot product is a scalar. With cross product, we need the magnitude bars because cross product gives us a vector. So we have talked about parallel vectors back in section 1 or section 2. Does anybody remember how we checked to see if two vectors were parallel? Slope. We checked to see if they had the same slope. Or and that was for two-dimensional vectors, if they had the same slope. If it was a three-dimensional vector, we would check and see if the ratio of the components was the same for all three components. So cross product is another way that we can prove that two vectors are parallel. So if u cross v equals 0, that's enough to prove that two vectors are parallel. Because if two vectors are parallel, that means that those are not two unique vectors that form a plane, that define a plane. We've got to have two unique vectors to define a plane and get one unique vector that's normal to it. Two parallel vectors do not define a plane. So if u cross v equals 0, that means u and v are scalar multiples of one another, which is definition of parallel vectors. So it's another way we can check to see if two vectors are parallel. We can do the cross product. What did we say the relationship was between two vectors if the dot product was 0? 90 degrees. If the dot product between two vectors is 0, then they are perpendicular to one another. And then the last one, we talked about this at the very end of class yesterday. The magnitude of u cross v is the area of the parallelogram that has u and v as adjacent sides. So the magnitude of the cross product will give that area. we are going to find a unit vector that is orthogonal to both u equals 2I minus 3j plus k and v equals I minus 2j minus k. So there's a couple different things we need to do. First, we're going to do cross product. That will give us an orthogonal vector. So we'll start with the cross product. It did not specify which direction, so technically it doesn't matter if we do u cross v or v cross u. So this time u and v are written with the ij's and k's. So what are the components that we're going to write in our matrix for u? Don't look at the board. Because some of the numbers are missing. Both of our k's don't have numbers in front of them. So just ones. And make sure you use the signs. Plus means positive numbers, minus means negative numbers. So for u, we're going to use 2, negative 3, 1. For v, we're going to use 1, negative 2, negative 1. The formula? You like it better? That's fine. I don't care how you do it. We should have 5i plus 3j minus k. So one of our tasks was to make sure that the answer was orthogonal to both u and v. So a cross product is always going to be orthogonal to the two vectors you plug in, but we were also told to make sure it was only 1 unit long. We wanted to make sure it was a unit vector. So now that we've got it pointing in the correct direction, we need to make sure it's the correct length. So how do we create a unit vector? Divide by the magnitude. So now we want to know what the magnitude of u cross v is and divide by it. So the magnitude is 5 squared plus 3 squared plus negative 1 squared. Radical 35. There is another vector that is orthogonal to both u and v that's a unit vector. What is it going to look like without doing any calculations? Negative 5 over radical 35i minus 3 over radical 35j plus 1 over radical 35k. Just pointing in the exact opposite direction, because they didn't specify to do u cross v or v cross u. They just said make sure it's orthogonal. So that one technically would be true as well. Questions so far? Joe, did you find your mistake in your cross product? Oh. I heard you say like you got 2 or something. Oh, yeah. Okay. Okay. All right.
So if I'm putting component form, that doesn't make it wrong, does it?
No. Nope. You could write it with IJKs, or you can write it in the pointies. If you write it in the pointy parentheses, you're going to leave off the pluses and the minus and the IJKs though. You just put commas. So so this one, you would write it just with the coefficients. 5 radical 35, 3 radical 35, negative 1 over radical 35. I have some people sometimes that try to mix them and put in the IJK in there. So don't do that. Yeah, either one of those is perfectly fine. All right, so somebody asked me about this on the homework. We are going to calculate and sketch a graph of K cross I. K cross I. So those aren't necessarily the names of vectors like u and v. Those are our standard unit vectors. So I would write them out and list out all three of their components, their component values. So it would make more sense as to what exactly I'm plugging in for each value when I do my cross product. Remember, k is the standard unit vector in which direction? Z direction. And I is standard unit vector in which direction? X. And in the right-handed system, we curl from the first one to the second one. And in here, Z goes up and X comes at us. So everybody with your right hand, Z is up, X is at us. What do you think the answer is going to be? Here's Z, and we're going to curl to X. Positive what? Positive y, which is J. Answer should be J. Answer should be J here. And it is. So let's show it real quick. So K technically is 0, 0, 1. I is 1, 0, 0. In component form as standard unit vectors. And we want to do K cross I. So we're going to do IJK 0, 0, 1, 1, 0, 0. So for the I's, we're doing 0 minus 0, which means there's no I component. For the J, I'm doing 0 minus 1. And remember, in the J, you put a subtraction in front. So it's going to be a positive J. And then for the K's, it's 0 minus 0. So there's my K and my I. If I take my hand, my right hand, and I curl from my K to my I, my thumb will be pointing in the positive y-axis, which is why my answer is positive J. You have to use your right hand because we're a right-handed system. All right, first, come here. Put your back to the board. Come here, scoot your chair.
Just flips.
So the X is going that way, okay? So that's why I've got my back to the board. Z is up. So that's where we're starting. And we're curling towards the X, which is out that way. So I'm curling down. Your thumb's pointing to the positive y-axis. Okay. Okay, you need to. Oh, need a break, don't we? I've got 2 more things to do in this section. We're gonna have a break first.
And
Unfortunately, I believe you.
a porta potty as well. We reject the porta potty.
All right.
Strap rockets. This will be the next page. Porta potty.
One of the common applications for cross product is calculating torque. And I didn't write my problem down, and it's out of my old book. So I'm gonna improvise a little bit. Torque is the moment of a force about a point and moment is the tendency of a system to want to spin. So technically, torque is a vector, and it's got a magnitude and a direction. We're typically just interested in the magnitude, but the direction is going to be perpendicular to the force vector and and our other vector, which is usually like a lever or something that the force is being applied to. And it's the axis that we're spinning about. So the example that we're going to look at is a pedal on a bicycle. So the pedal is on a bar that's connected to the center of the wheel. And then we're pushing with a downward force. Does it sound familiar?
Yeah, we had to solve a problem where we had to find the torque or speed of the rear spoke, but you had to calculate first the turn of the main one.
Mm-hmm.
On the pedal, on the main one, on the chain, it's the bevel. And then compare it to the older bikes where
You had the big front wheel,
Yeah.
the little small back wheel.
and
How many
other one-
revolutions does it take to go this fast?
That sounds awesome.
I know what you're talking about, but I did not do that part.
Did
I did it because it sounded something. That's the only problem I've actually done.
you say that's the only problem you've actually done?
Like by myself, like when I was looking at notes or anything. Just because I felt like
So this problem is nowhere near on that level. This is just a cross product
I
problem.
mean, radiant physics.
oh my gosh, I should.
So I didn't have this problem written down. I just had the page number that it was on in my old book. So I'm going to have to kind of improvise as to what it said. So a pedal is connected to the center of a wheel. By a 1-foot metal bar, and it's positioned at an angle of 60 degrees. A force of 50 pounds is applied to the pedal directly downwards. We want to find the torque. About a line running through the center of the wheel.
So we gotta use.
Yes. I guess so. It does sound like a unicycle. I told you I didn't have the problem. Could be a hand crank. It's an egg beater.
Yeah. There's no wheel, right?
Can you put 50 pounds of force on an egg beater?
You put a wheel on an egg beater?
There's a gear,
Yeah, that's not a wheel. That's the pedal.
but there's a gear in the middle.
That's the pedal.
No, the pedal is what you're holding to.
Yeah.
Should I change it to handle and gear?
No.
All right, you all are so picky.
No, we're just standing there.
I know. It's not a pancake.
No, it's pizza cutter. It's pizza cutter.
Brand of a wheelbarrow.
That's pizza cutter.
That is the wheel
You changed.
and the pedal and the bar at 60 degrees.
You just sit up there and ride on
No.
it. Where's the pedal? Is that the pedal up there? What?
Hannah's gonna be like, what the heck is going on?
No gates.
I kinda see it.
We're sorry.
I see
We're
what you're
sorry,
supposed to
Hannah.
Is it really that bad?
I see what it's supposed to be. I just don't get how it's gonna work.
It looks like the wheelbarrow.
It doesn't have to work. We're just doing a calculation.
The wheel is moving or is it turning?
The pedal's moving.
I understand it perfectly.
Just like, what the heck?
Oh.
We're sorry, Hannah. We did not.
So this red line is actually coming out at us and going back into the board or going back into the sheet. That red line is perpendicular to both the lever and the force. Okay? It's perpendicular. We will get that if we do the cross product. That is where the moment is. That is the axis that we're talking about. And the magnitude of that is the torque. We want to know the tendency of the system to want to spin around that axis. So we need two vectors. I need a vector that represents this, and then a vector that represents the force. So a vector for the pedal and a vector for the force. So the pedal is only 1 unit long and it's at an angle of 60 degrees. So we're given a magnitude and a direction, but we need to write it in component form because to be able to do the cross product, we have to write individual components. So we've got to go all the way back to section 1 where we talked about switching between magnitude, direction, and components. So how can we change a magnitude and a direction into X and Y components?
Magnitude, cosine.
So X is magnitude times cosine of the angle, and Y is magnitude times sine of the angle. And cross products are always done in 3 dimensions. Potentially.
Okay.
You could potentially, I'm just, using cross product. So I'm thinking of this as just being in the XY plane, but we need to have 3 in order to do cross product, so I'm just putting 0 for the Z. And then F is straight down with a magnitude of 50. So straight down is what direction? We don't necessarily need to do degrees, but that's correct. We don't need an angle. Negative J. Yeah. We could just go straight to negative J. Since there's no X component at all with straight down, we could throw all of it. We would say 0I minus 50J and 0K, since it's just straight down. And it has a magnitude of 50. So we've got a pedal that's being pushed straight down, and we want to know its tendency to want to spin at its fixed point right there. So the moment has the magnitude and the axis it's spinning around. The torque is just the magnitude. So we want to do the cross product. And it turns out to be a pretty easy one. What is cosine of 60?
Square root of 2.
No,
Oh, 1/2. Yeah, pi over 3. 1/2. Yeah.
it is a half. Sine of 60 is square root 3 over 2. And then we have 0, 0, negative 50, 0. There's so many zeros in there, this cross product actually goes pretty quick. The I just ends up 0. The J ends up 0. And the K ends up negative 25. It's negative because I've got this as my x-axis and this as my y-axis. If we compare that to how we normally have been drawing our x and y axes, we are actually spinning clockwise instead of counterclockwise. Typically in trig, positive is counterclockwise. But we're pushing down on this right now, and that's clockwise, and that's why it's negative. The torque is just the magnitude for this guy. Mhm.
Let's go a smash.
I'm gonna say no.
Torque isn't the direction of this force.
Torque is just a magnitude. Torque is just a magnitude. I think you can do negative and positive to indicate who's doing the work, because it's like a foot-pounds. It's like foot-pounds of work, and you could either be gaining work or losing work. If you remember in Calculus 2, when we did the problems where we were emptying a tank, we could actually apply a machine to the tank, and we could have to give it gas to do the work, or we could just poke a hole in the bottom and let gravity do the work, and then as the water spilled out, kind of harness that energy with a water wheel or something. So we could either have to put work into it to get it out, or we could let gravity do the work and we could gain energy from it. Maybe that would be a way that it could be positive or negative, depending on who's doing the work. So you'd have to maybe say whose perspective we're looking at it from, possibly. So the cross product as a vector also includes that axis that we're rotating around. And that's the moment. And then when we just look at the magnitude of the moment, that's the torque. So the moment includes the axis of rotation, and then the torque is just the magnitude of it. All right, last thing real fast, because I want to tell you one quick thing from section 5 before we leave. I'm going to have you guys try this by yourself really fast. It's really easy. It's called the triple scalar product. So we had it in our algebraic properties earlier. That just said if you wanted to change the order, you had to move the operation with it. You have to do the cross product first, the dot product second. Technically, we could do all of this in one calculation by replacing the ijk row in our cross product with the u components. Because when we do that dot product second, all we're going to do is multiply corresponding components. So we would take the I component from V cross W and multiply it with the corresponding component in U. And that's exactly what we're going to do here when we do the determinant of this 3x3 matrix. So we could do the whole entire thing at once if we wanted to. This gives the volume. You want to learn a new awesome word? The volume of the parallelepiped.
English.
It is English. With U, V, and W. As adjacent edges. So a parallelepiped is like a rectangular prism. It's like a box, except all of the sides are parallelograms.
It's like a jello cube. It's like a smack jello.
It's like a cube with those pots.
We're so close. I started like this. I just got 2 countries. Argentina's closed all the way. Oh, man. The United States is freaking Argentina. It's the only thing that the United States closed everything down.
I liked my first one better.
Me too.
Cream cheese. It's cream cheese.
What are you trying to get? The first one was good.
Something's missing.
Oh my God. Nash can't right. Nash can't right.
That's the Nash, that's
Oh, you
the,
can't draw.
that's the Nash County parallel.
This is why we have AutoCAD.
It's not solid. Is there anything consistent with cream cheese?
You almost need to start in the United States.
Whoa, what just happened?
Oh, what we've done today.
I know we've done a lot.
I'm trying to think of a wrong with endemic disease.
What is it doing? Why does it keep going to the top?
It's time to be done. That's
It is not time to be done.
That's what I'm saying.
It's the Russians, I tell you.
Look, we got 9 minutes to it.
It's the Russians, I swear.
All right, I'm drawing this one more time.
Sure, she's still drawing a picture. Couldn't you find the like shape or something? You know what's really about it? You didn't put a T on it.
I probably did, and I kept hitting back so many times.
That was like no.
I did because it took edges off also.
Why is it this? That's a cube. The rectangular prism.
Nope, it's slanted.
It's not.
I'm keeping it. We gotta move on.
Everybody just draw a key.
That seems like a rectangular prism.
You guys talking about cheesecake?
We're arguing whether cheesecake's a pie or a cake.
It is,
No, cheesecake's actually just a filling, and it can be prepared as a pie or cake.
it is a cake.
Hell yeah.
You can make a cake.
She's the teacher, she.
But what if cake? It's a filling, what mean?
Adam, it's just a game.
That's called freaking
Icing,
icing, man. I guess sprinkles the cheese.
What course they gonna play? They only have one course.
Keep those. It's like saying chocolate is a cake. But all cake has, icing doesn't.
It has a batter that goes in a
Am I
pan
gonna need more room for this?
that, no,
No? You sure?
that has to bake and rise and
See, that's not cake. I mean, that's what cake is, but you don't.
cheesecake does that too.
I have to do the instant one. I mean, just.
That's not cheesecake.
That's not good though. That sounds good though.
Breathe that. Breathe that stuff.
Little message. word that. So your subliminal messages that work.
Hopefully it's just the internet. Hopefully it's like an entire.
All right, 514, 302, 131.
6, 7, 5, 3, 5.
They are going to form a parallelepiped. Bonus points if you draw it.
Can I just draw
This
it?
isn't graded.
Probably part of the problem.
Since this isn't graded, then I can work. Well, you never told us what to do with triple scaling. But you just gave us the matrix. What are we doing with it?
Those straight lines on the side means determinant.
I heard that, but like, was it? I never did. I never
Find
did
the
matrices.
determinant?
I never did matrices.
Oh, cofactor expansion,
So,
like what we did with the IJK, except instead of the IJK, you actually have a number out front. So when you do the inside diagonals, and you get just a number from the 2x2s, instead of multiplying it by an I, you'll actually multiply it by a number.
I'll just
And you'll end up with one final number at the end.
Which number you multiply?
What is it? I'll watch much there.
If I come up with the I row, or I column, is it still like that?
Yes.
And so then I would do like V2 times W3.
And instead of an I in the front, you're going to have a 5 in the front. Yep, so we've got U in the top, V in the middle, W in the bottom. And we're going to do cofactor expansion exactly the same way before, except instead of IJKs in the front of my 2x2s, I'm going to have 514 in front of my 2x2s. So I'm going to start with 5, cover up 5 row and column, and I'm left with 0, 2, 3, 1. And then I'm going to go on to the next one, which is 1, and you change the sign. Cover up 1's row and column, and you're left with 3, 2, 1, 1. And then go on to the 4. Cover up 4's row and column, and you're left with 3, 0, 1, 3. And now do your 2x2 determinants. So I've got 0 minus 6. Ooh, why is that on? And then 3 minus 2. And then 9 minus 0. So that's negative 30 minus 1 plus 36. Which is 5.
That's the volume of the parallel.
So the only difference is we had IJK here before, and we had to leave it as 3 separate terms. So now we got numbers there, and we can simplify it further.